could I introduce Tadej Rojac from JSI, who's going to be talking about bismuth ferrite-based piezoelectric ceramics.
Thanks a lot. Thanks for the introduction. So I'm going to talk about bismuth ferrite and some other piezoelectric based on this material. The talk will be a bit different than what you heard in the last 2-3 hours. I'll not talk about measurement techniques. I will somehow follow, I think, the talk by Tim when he introduced these processing issues in these BiFeO-based materials. And I will somehow start with this, and then the second part is more devoted to the piezoelectric response of this kind of materials. This is the outline. So I will start with processing. This will be the main part. I would like to, there are several things here which are important. I would like to stress two. One is this effect of impurities. You know, when you make a material, you want always to work with those oxides that you think that you want to prepare your perovskite, but you usually always work with some impurities, some third, fourth components, which can have this, then at the end, a very high effect, very large effect on properties. I will show in BiFeO this is extremely important to take care of these impurities because they not only affect properties, but they only, on a quite large extent, affect the phase composition of your final ceramics. And then second will be reaction kinetics, which is very general. We are here working with solid state synthesis, so I will talk about diffusion and some secondary phases and so on. The second part is piezoelectric response of BiFeO. I will concentrate here just on one specific, I think, issue, that's conductivity. I'll not talk about conductivity in terms of conductive path that goes through the whole sample, but I would like to stress on certain local conductivities, that local conductive paths that are not necessarily percolate the samples. For example, you can have some local conductive paths within grains, and I will show that this may affect also the macroscopic overall electromechanical response with this example of bismuth ferrite. I think it's important because this effect can be also present in other BiFeO-based materials. So I'll start with processing. These are, well, those that work with BiFeO, I think you're familiar with this sort of microstructures. So these are the secondary phases that are very usually present when you sinter the BiFeO. This dark region, which is the iron-rich phase, and this bright regions, which is the selenite, the bismuth-rich phase. These are the two phases that also appears in the phase diagram. Sometimes it's good, and that's one of the messages, that one looks at these secondary phases, how they appear, because they appear differently in a different form, and you can get some information, some data, some clues of why they are formed there. For example, these are two batches of BiFeO prepared in a very similar way. In one case, we saw these huge mullite crystals in which you have this selenite phase embedded inside, and you can see that there are contacts between secondary phases. It looks like they don't want to react further. They're stabilized there, and that can be explained, as I will show you later, by phase diagrams. In some other cases, you have these small inclusions of the iron-rich phase and the bismuth-rich phase, which are somehow separated, and this can be also related with some reaction kinetics and so on, which I will talk later. When you want to take bismuth ferrite and integrate it on a substrate, let's say with some electrons as a thick film, things become even more complex and more difficult. This is, for example, a case when we wanted to deposit BiFeO on a substrate. After cooling, basically, after heating, basically, you get just the secondary phases with any sign of BiFeO. Here, problems are others, interface reactions, diffusion through layers, and so on. This will be in more details presented by Genia Komekova on Tuesday on a talk, and you will see all these kind of problems when you want to integrate this sort of BiFeO materials on a substrate. So I will somehow talk about two things. One is thermodynamics with phase diagrams, and the other is kinetics. You will see here that you have to, when you work with BiFeO, for example, when you think that you have a binary system between bismuth and iron oxide, it's mostly never the case because you almost always have a third or fourth component, which is your impurity, and I will show an example with silicon oxide. And then is kinetics. So we are working with solid-state reactions. The solid-state reaction basically work on diffusion, and very often you will have some of these secondary phases that may be stabilized just because the diffusion is incomplete at a certain temperature. So I start with these impurities and phase diagrams. So in general, the effect of impurities on the properties of ferroelectric ceramics is well known. I'm showing here two examples. One is this barium titanate single crystal from Ren paper, in which he showed this large strain that is reproducible, and that's basically related with switching of the domain walls by application of the field, and then these domain walls will somehow be pulled back in the initial configuration with the zero strain, and because of some complexes, effect complexes that are present inside the material. In this case, this is acceptor, basically acceptor site in a pair with oxygen vacancy. But they claim this paper, and this is quite general, this iron basically is present as an impurity in a nominally undoped barium titanate with very low concentrations, and you can see how an impurity can have a huge influence on how the material behaves in terms of macroscopic properties. Another example is BiFeO. This is our case from our lab. For example, in this case, in this black case, we try to measure polarization as a function of electric field. You see this sort of balloon here, which just tells you there is a huge contribution of an out-of-phase component in the polarization response, which is related with conductivity. And then you have just 0.1 weight percent of cobalt. You can basically come to this accidentally. We got cobalt during processing, and then we just repeated to see if this is exactly the case. And you see how then we can, just with this bit amount of cobalt, measure, let's say, a normal dielectric response with a bit of hysteresis. If you measure here current, for example, we were able to see at certain field 4 orders of magnitudes in the current response between BiFeO and the other when you just added a bit of impurity. So this is a problem. Purities in a relatively low amount can determine a lot your processes, properties. In all these cases, the show we usually basically assume that this impurity is going in the perovskite, somehow incorporates, it makes this oxygen vacancy or whatever. But in the case of BiFeO, especially when you're processing BiFeO, one should think about incorporation of these impurities also in a different way, because the same impurities can also go not only in the perovskite but in the secondary phases. And this is where you get to this phase diagram here. Basically, you're switching from a binary phase diagram. This is what you want to have, but in reality, you should have, let's say, an impurity. That's the case of silicon oxide. We have a ternary phase diagram, and the silicon oxide will be incorporated into the bismuth-rich phase. So it will form its own bismuth-rich phase, the selenite one, which will have a certain solid solubility with the iron one, and this is how the tie line goes, like shown here. Basically, you get a very tiny and very stretched triangle here in the phase diagram. It's very stretched, which means that when you're with the composition here with a bit of silica inside this triangle, you will basically have all 3 phases. This one, the selenite and the bismuth ferrite, in thermodynamic equilibrium at that temperature. So this is phase diagram. And the problem is, since this triangle is very stretched, just a bit more amount of silicon oxide will basically have a huge influence on the composition, just because the triangle is very tiny. That was also confirmed experimentally, and I think this is one of the main, among others, one of the main problems in the reproducibility of bismuth ferrite, because taking care of impurities and control the amount and type is usually very difficult. So how to avoid this issue? Well, the first thing is to take care really about impurities. Go very carefully when you prepare the oxides. Start with very pure oxides, which are besides that very expensive, and try really to maintain during the process very clean conditions and so on, to try to avoid these very low concentrations that can, for example, of silica, which is a very standard impurity, that can so largely affect your final composition. Well, there are other cases where this problem is somehow solved by itself, in a sense. When you start to modify the bismuth ferrite chemically, for example, with samarium, the concentration should be high enough. You basically go in a ternary system, and that changes the phase relation. So we are now basically, if you have silica, you have now quaternary system, bismuth, iron, samarium, silicon. Could be very complex, but still different than in case of bismuth ferrite. And here is an example, experimental, between, it's a comparison here between 2 batches that were prepared in exactly the same way, in which we got some silica contamination. We still don't know the origin, but we found it by EDS analysis at SEM. And here in case of BiFeO, you see that we have plenty of secondary phases. We found the silicon basically in the gamma phase, and that confirms very nicely the phase diagram that I was showing before. While in the case of samarium-modified BiFeO, we found this same silica in the samarium-rich phase. So you see that once introducing samarium, it uptakes silica, changes completely the phase relations, and this is how the problem of silica somehow disappears in other systems. That's generally related with phase relations and phase diagrams. The second thing, besides these impurities, is kinetics. So this is BiFeO, this is now well known. Basically, there was some study done by Bernardo and co-workers on a diffusion couple study. They showed that bismuth diffuses faster than iron, so basically have a diffusion of bismuth and oxygen toward the iron-rich core. This is the reaction sequence, you know, the selenide phase is formed, and then the iron-rich phase, and then bismuth should somehow diffuse toward the center to complete the reaction. And this might not happen at certain temperature, because the fusion path becomes too long. It will not happen, and you will have this image like here when you have this selenide phase at the grain boundary, this iron-rich core, which is stabilized kinetically. It's just that the reaction stops at a certain stage. So this is another view of how this secondary phase may be present in the final ceramics. This case of BiFeO is pretty simple. It's still tough to prepare a phase pure BiFeO, but it's relatively easy to understand. Now, when you go to complex system, when you start to modify heavily bismuth ferrite, for example, by making very solid solution. These are some examples from the literature. We heard something about the system today by Tim. There are some others. Things get much more problematic because now you have basically several components, several oxides with very different diffusion coefficients, and things become complicated. I will show an example on this system with which we work right now, with this family of bismuth ferrite and alternate earth titanates. And I think it shows, in principle, what is the major problem of perhaps all or many of these kind of materials. And it's basically it's nothing new. It's something that was already discovered years ago. It's a general problem which I'm repeating because I think it's important. When you have, let's say, like in this case, 4 components: bismuth, iron, strontium, carbon, and titanium oxide, you would like to have low particle size, narrow particle size distribution, and you want to mix them homogeneously as much as possible. In this case, in multi-component system, that's basically the point. Having a homogeneous mixture of 4 components is not good. This is simply because you have all possible contacts inside the powder between, I don't know, bismuth, strontium, bismuth, iron, all 3, for example. And that creates sites at which certain intermediate phases, either binary one, for example, bismuth, strontium, bismuth, iron, and so on, can be formed. And this is experimentally what we exactly observed. This is an X-ray pattern of the mixture of these 4 at different temperature. You can see that there are several phases that are formed. These patterns are very complex, so we were not sure about all phases, but we know that it's a multi-phase mixture. Some phases appear at higher temperature than others. For example, here we have this bismuth strontium solid solution with a relatively low melting temperature, and that's dangerous, as I will show later. Of course, when you increase temperature, as you increase, you will get more complete reaction. At a certain stage, it will stop. That's related to diffusion controlled reaction, so it's fusion limited. At a certain stage, it will stop. If you, for example, try to double calcine, it will not work. It will still have some secondary phases. So what usually you do, you press the powder, you go at high temperatures to sinter it, and you hope that these secondary phases will then react once you go to higher temperatures. And this is exactly what happens, apparently, when you look at the X-ray diffraction pattern. After the sintering at 1025 degrees Celsius, you see that it's phase pure. So you're happy, and here when you can take a sample, put electrodes and start to measure, this is the most exciting part. Well, the message here that I want to tell is this is sometimes very dangerous. One cannot ignore all these phases that are formed when you heat the material at a certain temperature, is that especially in this bismuth ferrite, and I would also say generally bismuth-related materials, they tend to form these bismuth-rich phases with usually very low melting temperatures. And this is an example of the same ceramics that was X-ray diffraction pure, seen on a microscope and with a backscattered image that's sensitive to the phase composition. We see this situation classical for diffusion control reaction, where you have a phase at the grain boundary and a certain inhomogeneity inside the grains, very similar like in BiFeO. IDEAS shows that this phase is basically an bismuth-rich phase. And TM confirmed that the phase is amorphous, so it's a liquid phase. At a certain stage, we had some phase rich in bismuth that did not react before we exceeded its melting temperature. So basically, you want that it will react, but during this way, let's say, it will melt, desegregate, met the grain boundaries, and this is how you end up with such ceramics. So. Sometimes it's useful to see when you work with such complex systems. You don't have all phase diagrams with which to check this, but it's instructive to check the binaries, for example, in this case between bismuth and strontium, bismuth titanium, and bismuth iron oxide. And you see that you have at least three things that might be critical when you try to synthesize this material. For example, in the case of strontium oxide, you get the solid solutions, which will vary in melting temperature as a function of strontium content in the solid solution. You have usually these selenide phases, so iron and also titanium will form the selenide phase with bismuth, this bismuth-rich phase, and very often, like the case in the iron, this phase will very technically decompose to melt in bismuth oxide at a temperature that is even lower than the temperature of bismuth oxide, the melting one. So this temperature can be really below 800 degrees Celsius when you typically calcine your samples. And you have these various tactics here with very low melting temperatures. And it's sort of rule of thumb, if you have the temperature of a ternary eutectic are usually lower than of a binary. So when you add the components, you can really create very low eutectics temperatures, and this will then melt. If it's melted before it will react, it will create these problems with this liquid phase around the grain boundary, which of course you don't want. How to solve the problems? We thought about two simple things. One is what you can do is to make a homogeneous, better mixture of the initial components, ideally with very small particle size. And go these solid-state reactions are basically related with fusion paths, the fusion distances. If we have very small particles, this means that the reaction will be completed basically at lower temperature. And this we did by high-energy milling. It's basically conventional milling technique in which you just not add these liquids inside, and you get a very homogeneous mixture. And basically, it looks like we didn't see any liquid phase around the grain boundaries based on SCM. It's the same picture as I showed before, declining in the same way, which tells you that probably these liquid phases will somehow react before they get melted. You can never get rid of with the formation of the secondary phase because you always have contacts there. But you should allow that they react before you go to syntacon. And this is another case. The second possibility is just don't use bismuth oxide in the initial mixture. This will prevent forming liquid phases because you don't have the main component, the BiDeO3. So what you can do, for example, is to prepare perovskites before and then mix together. And as you can see, it works very similarly like the mechanical activation. There's some difference here in densities, but this is meant to show the principle of how you can avoid with this bismuth-rich low melting temperature liquid phases. Okay, I will, that's for the first part. I will now switch to something that is maybe not so much related with the first. Basically I'll talk about, try to show you some correlation between piezoelectric, macroscopic piezoelectric response of BiFeO and local electric conductivities. So you probably know that BiFeO now, I think there are something like 3,000 and more papers on BiFeO published in the last 10 years. People really tried a lot of preparation methods, and this very often ends up to have properties that are just paper dependent or case sensitive. You can see here, for example, a table when you can see a piezoelectric coefficient between 2 and 45, so there is a very large spread of data. This is known because BiFeO has high coercive field, which is coupled to very high electric conductivity, and that's one of the main problems. Of course, also processing. What people do to report this, usually this polarization electric field loops, a subswitching one, and I will show you that this sort of loops then can give you also the one which relates mechanical electrical variables, can give useful information about how this material behaves piezoelectrically. So this is the piezoelectric coefficient as a function of frequency. It was measured, the converse one, it was measured with a fiber optic sensor as a function of frequency. The main point and the most, let's say, the particular thing in the response of bismuth variety, it has a very strong frequency dispersion above 1 Hz. For example, D33 jumps for a factor of 2, and then you have this piezoelectric phase angle, which is the phase angle between the strain and electric field response, sinusoidal ones, that is getting very, very high for a factor of 4. This is something that is different, for example, than PZT and many other materials, something similar than lead titanate, but I will show you it's a bit different. And this gives them this loss in piezoelectric loops if you want at very low frequencies. The same mechanism, this frequency dispersion, this brute frequency dispersion at low frequency is also responsible for the temperature instability of the piezoelectric response in BiFeO. So what basically happens is this frequency dispersion relaxation shifts up by increasing the temperature. And if you work, for example, at 100 Hertz, you try to measure the response. At a certain point, this D33 tangent delta, the piezoelectric phase angle will just increase up because this shift of the relaxation higher frequencies with the temperature. So, of course, we don't want this instability, and that's one of the reasons I think that one should go in more details to see where is this effect coming from, why this happens. So the next parameter that's usually used to measure piezoelectric response is the amplitude of the electric field. Here the same curves as before, D33 and phase angle is a function of frequency, usually with the same technique. But we here change the amplitude of the sinusoidal electric field in the whole frequency range. And you can see that we have here a strong dependence of the piezoelectric coefficient in piezoelectric phase angle with the amplitude, which tells you that basically you have some nonlinearity coupled with hysteresis. And this is typically attributed to this domain wall, irreversible domain wall contribution, which is quite extensive for macroscopic properties in BiFeO. Now, what is the main difference? This is also happening in PZT, we know, but what is the main difference is this piezoelectric nonlinearity with hysteresis somehow manifests differently than in PZT. For example, PZT, you typically measure nonlinear responses in all frequency range, quite let's say, in a fashion like seen here with this logarithmic dispersion. BiFeO, we see that this nonlinearity sets only at very low frequencies. So these domain walls will contribute to properties, they move, they contribute to macroscopic D33, but they're somehow restricted only to low frequencies, so they need time to move. And this is, if you just think intuitively, you would see that there might be some correlation between domain wall motion and conductivity, because these are the frequency when conductivity processes inside the material are becoming important. So, as a possibility, we check that since there is a coupling of domain wall motion and conductivity, could be, for example, through having the domain walls themselves that are conductive. We try to check this by a combination of SEM, PFM, and AFM analysis. So this is the BiFeO sample, the main structures. We have these large regular domains. We also measured local conductivity to see if really the domain walls are conductive. So we take a tip and then you travel around, with the AFM tip, and you apply a constant DC and you measure current. And we always, whenever we cross the domain wall here, we saw a spike in current, which looks like there is some conductivity at these interfaces. We check this then with various other, within IFM, with various other, let's say, ways. One is, for example, as I said, to scan, you see that if you have a spike when you cross the domain wall. Sometimes one must be careful here because you can, with the field that you apply, you may at the same time move the domain wall, and that can give you, this transition displacement current. So this is, for example, checked by sitting with the tip for a long time, measuring very long time, as much as possible, the current, and we were always able to see that there is the current at the domain wall which is higher than inside the domain, which tells you that probably is related with the higher conductivity of the domain wall itself. And there are some other ways. So we think that this conductivity of the domain wall that was first discovered in thin films and looks like they're also present in bulk ceramics may have this huge influence, this large influence on the electromechanical behavior, which I think that it would be important also for other maybe BiFeO-based materials in the future. This is the mechanism, it's called nonlinear Maxwell-Wagner effect. I think Dragan will explain this in the tutorial in much more details. In general, this works, how it thinks it works is that you have different grains in your ceramics that are differently oriented. They have different piezoelectric coefficient in this direction, that's obvious, because D33 is a function of orientation, and there are other reasons for that. When you press, for example, such a material, you will have some piezoelectric charges which will not be uncompensated totally because you have different piezoelectric coefficients. And then from this you will create internal fields. And that internal fields will in turn give you some additional charge, dielectric one, which adds up to your piezoelectric one. The problem becomes with this term here, these charges start to change with time, start to drift. And this can happen, for example, because we have conductive domain walls. So basically we'll have, in addition to this term can also become basically dissipative. You can get a relaxation in this term, and since these two couple, then you will get this huge phase angle and piezoelectric behavior at low frequency. So basically, the coupling between conductivity and piezoelectric response comes from the fact that in these materials you have always electromechanical coupling, and this conductivity basically can make a dispersion in the dielectric term, let's say, which will be somehow transfer to the electromechanical behavior. This is how we think this specific effect can be explained in BiFeO. And it's a very temperature dependent because both conductivity and the domain walls will start to move more at higher temperature, and then is this problem with temperature stability. Okay, I will conclude here. So I hope I showed you a few things that I think are important. The processing of BiFeO, so one should take care about these impurities, about these liquid phases, how powders react, and so on. And then I tried also to show that this BiFeO has a specific piezoelectric response, very different than in other materials that we well know, for example, such as PZT, and it looks like it's correlated or it's related to these conductive domain walls which are present in this material. Thanks.